So, continuing with our previous lecture, in this lecture we shall actually be seeing some examples and we shall see how we can write test benches in various different ways. Okay. So, writing Verilog test benches is the topic of the lecture. So, in this lecture, as I said, we shall be illustrating various ways of applying the stimulus using examples. Specifically, we shall be looking at the following things. We shall see how we can write test benches for combinational designs. Not only that, how we can apply the test patterns, how we can generate the test patterns. Then similar things for sequential designs. Generation of the clock and synchronization of the inputs is very important, how we can do that. And also we shall talk about that how we can automatically verify the output generated. Like for example, let us say I am designing an adder. My test bench should be such that it is applying the inputs, it is reading out the output, and it will automatically compare whether the output is coming correctly or not, and it will just tell me that the design is good or bad. So, it will not just show me a list of all the inputs and outputs, it can also tell me whether the output is coming as per the specification or not. Okay. And lastly, we shall also look at how to generate random test vectors, which may be useful in many test bench applications. Fine. Let us start with a very simple example, the simplest example, a full adder. So, we have a behavioral description of the full adder using assign statement. So, S and CO are the sum and carry and ABC are the inputs. So, sum is the XOR and carry is AB or BC or CA. So, let us see different ways of doing it. This is the first approach, and this kind of test bench we have already seen earlier. And so, what we have done, this was our full adder module. We have instantiated the full adder module, we call it FA. So, we have specified the parameters in the same order, sum, carry, ABC. Here we are calling it SUM sum, COUT carry out, ABC are the inputs. So, the inputs we are declaring as reg as usual, and the output sum and Cout we are declaring as wire. So, here because it is a combinational circuit, we are making it simple, we are using a single initial block. So, we are executing monitor only once. Here you are saying we want to display time, we can also give it in the beginning $time comma, you can also give it like that. So, there the time will be displayed in the beginning like this. Then within quote A equal to, B equal to, C equal to, sum equal to and Cout equal to, all B, B means binary. We are displaying these 5 things. So, you recall monitor means these 5 variables will be displayed whenever at least one of the variables they change state. Okay? Fine. So, the first input I am applying is A0, B0, C1. Then I change B to 1. So, delay is 5. So, after delay of 5 I am doing this, then A equal to 1 and last factor is 0 0 0 and then after another 5 I finish. So, let us see the simulation output what we get on the screen if we run it. So, initially, so whenever the time is initialized to 0, that will also be a change. So, A, B, C, sum x all are undefined, all are x. At time 5 I have initialized. At time 5 A becomes 0, B 0, C 1 and my sum becomes 1, carry is 0. Then 10 I make B equal to 1. So, now B is 1, A 0, B 1, C 1. So, now sum is 0, carry is 1. So, again after time 5 A is 1, this is at time 15, A is also become 1, 1 1 1. So, sum is 1, carry is 1 and at the end all are 0. 0 0 0, sum is 0, carry is also 0. Okay. So, this is a very simple way of generating these tests. Now, the same example I am showing in a slightly different way. So, in the earlier case I had used a monitor, of course, this is more convenient, but I am just illustrating the use of display. So, instead of monitor, here what I am doing, you see, same full adder instantiation, I am just declaring inputs and range, the outputs as wire. Here I apply the first input A0, B0, C1, then I apply a delay of 5. Okay. Then I display what? Time A, B, C, sum C out, T equal to percentage 2D, A, B, C, sum B out, these are all B binary. Display will immediately display this line, T equal to 5, A 0 0 1 1 0. Then B equal to 1, again a delay of 5. So, now B becomes 1, again after a delay of 5 I put another display, same line. So, the next line is displayed. Then A equal to 1, there is again a delay of 5, again display, third line. Then again A0, B0, C0, again delay of 5, again display, fourth line, and then finish. So, you see that if you give monitor we need to give only once, and whenever the variable changes, the simulator will automatically understand that well, we are supposed to monitor the variables and we want to print it. And display means wherever I want the values to be printed, I insert a display command like that, just like printf in C. So, in this example I have inserted 4 printf statements corresponding to the 4 display statements, and for the display statements 4 lines are printed. This is the difference between monitor and display. So, in a test bench I can use display if I want, I can use monitor I don't. See one drawback of monitor is that if over a long period during simulation variables do not change their values, nothing will get printed. But I want to see that after every gap of 50 what is the outputs coming, I want to see, then I want to give a display, that irrespective of the values whether they are changing or not changing, I want to see their values, then I have to use the display command rather than monitor. Okay? All right. Now, the third example, same full adder, here let us say I want to generate all 7 inputs, like the simulation output, let us see, then I will see how we have done it. Say starting from 0 0 0, 0 0 1, 0 1 0, 3 4 5 6 7, all 8 combinations I want to generate and I want to print the outputs. Here I have used a for loop for the purpose. Well, how have we done this? It is quite simple. We have declared an integer of type I, because this A, B, C, these are 3 variables, all right, but we can treat them as a 3-bit number. If we concatenate them A, B, C taken together like this within this concatenation operator, they can be treated as a 3-bit number. So, in 3 bits numbers can go from 0 up to 7. So, I am writing this for loop as for I equal to 0 up to I less than 8, that means up to I equal to 7. At the end of every loop I equal to I plus 1. So, I 0 1 2 3 4 up to 7, and I just write a statement like this, concatenation A comma B comma C equal to I. So, this will automatically convert this number I into binary and assign the corresponding last 3 bits to A, B, C. This will be done by the simulator automatically. Okay. So, the values will get assigned automatically, this like this, and after delay of 5 I am displaying. So, in the display the time is showing us 5, 10, 15 like that. I am displaying the current time A, B, C and sum and count. Okay. So, you can see this is quite convenient, because the second approach was a little cumbersome, I had to use so many display statements. But in a loop, if I use this display, I am just writing display only once, but in a loop the patterns are getting generated automatically. Okay. There are 8 patterns I am generating 0 to 7, right. Okay. Now, this is the same for loop version, but we have just included dump file and dump files command. Now, I want to dump them to a file also. So, we want to see the simulation output in addition. Okay? This is the change we have done. So, let us see, we have specified that we want to dump them into a file whose name is fulladder.vcd, and we have given a statement dumpvats 0 comma test bench. So, what is 0 comma test bench means? 0 comma test bench means that in this module whose name is test bench, whatever variables are there, you dump all of them. Okay? So, here, so when you write dumpvats 0 comma test bench, so here the variables are a, b, c, sum and c out, all these 5 variables will be dumped. Okay? So, well, just I recall one more thing, that I asked you earlier that you can carry out simulation using the iVerilog tool, the iKeras Verilog, and you can view the waveforms using GTK wave tool. So, just for this example, so let us say my original file was fulladder.v and the test bench that I wrote was fulladder_test.v. So, for simulation, what are the commands I am giving? First, I am writing or I am invoking iVerilog. This is a command line parameter. So, I have to open a command window, I have to give it. So, I have to give an output file name. Let us give the output file name as adder. Then I give the name of these two files, fa.v and fa_test.v. Well, after this, well, if there are any errors, it will show errors. If there are no errors, then the next command you will have to give is vvp, this file which is generated, adder. So, once you give this, then the simulation output will be generated. You can see it on the screen. Now, if you want to see it on the waveform, if you want to see the waveforms, then you will have to invoke GTK wave. GTK wave. See, here we have given a dump file called fulladder.vcd. Okay? So, you will have to give the name of the VCD file, GTK wave fulladder.vcd. Then the window will be opened. So, you can click here, you can pull down the variables you want to display and you will see the waveforms here. So, let us see how. So, the first thing is that once you simulate it, once you give the VVP command, you will be getting the simulation output like this. Now, when you run GTK wave, you will be getting the waveform like this. Let us try to understand this waveform generation here. You see on the left, here you see the test bench, which is the name of the module. Under it, there was a module which was instantiated called FA, fulladder. The variables which are there, they are all mentioned here, A, B, C, CO and S, and these 5 variables are being displayed in the axis of time. Let us go back to the previous one. You see, this was the simulation output. At time 5, you applied ABC 000, at 10 you applied 001, 15 010 and so on. Okay? Let us see whether it is happening. This is my time t equal to 0. You see A, B, C, they are all 0 0 0 here. Okay? At time t equal to 5, this C is becoming 1. At time 10, B is becoming 1 and C is becoming, so 0 0 0 0 0 0, here it is 0 0 1, here it is 0 1 0, then it is 0 1 1, then it is 1 0 0 4, 1 0 1 5, 1 1 0 6, like that it will go on, right. And the sum and carry you can see, let us for example, if it is let us say 1 1 here A is 0 1 1 0 1 1. So, sum is 0 and carry is 1. And here 1 1 1 ABC all are 1, sum is 1, carry is also 1. So, you can actually look at the waveform and you can verify the functionality, you can see the times also, right. Okay. Let us take another example which is a sequential circuit. This is a 4-bit shift register. Now, earlier we have seen that how we can use the non-blocking assignment statement like this to create a shift register. So, I am showing the same example here. So, it is a 4-bit shift register where the input is A and the final output is E and the intermediate flip flop outputs are B, C and D. So, the description was, I am repeating. So, whenever there is a positive edge of the clock or the clear is negative, it is negative clear, 0 clear, you execute this block. So, if the clear is 0, then you initialize all the flip flops to 0, else you carry out a shifting, D will go to E, C will go to D, B will go to C, A equal to B all together, because this is non-blocking. So, the 4 flip flops they are appearing. So, they are B, C, D and E, this is B, this is C, this is D and this is E, and you are applying A from outside, right. This is how the shift register is supposed to work. Now, for this we want to write a test bench. This is a test bench we wrote. Let us try to understand what we are trying to do here. See, in this shift register, the inputs are clock and clear, okay, and the others are the outputs A, B, C, D. So, we have instantiated the shift register, clock and clear, this A and E, here we are calling it in and out, right, fine. So, this part I am explaining. Here let us see what we are trying to do. We are trying to apply some inputs 0, 0, 1 and 1. Like we have a 4-bit shift register, we are trying to apply first a 0, then a 0, then a 1, then a 1, and we want to shift these 4 bits inside the register. Okay. Now, you see one thing we have to ensure in the shift register description, we had here we assumed that it is triggered at the positive edge of the clock, pause edge. Okay. Here I am calling it CLK. So, you see, suppose my clock signal is coming like this. So, the shift register is supposed to be shifting at the positive edge of the clock. So, what I must ensure is that before the positive edge comes, before that here, before that my input must be stable. Okay, here I have only one input A must be stable. So, what I mean to say is that it must not be like this, that this signal A, let us say this clock we are applying, and at the same time this signal A which is there, it should not happen that A is also changing at the same time the clock is coming, because whenever the clock is coming, if A is also changing at the same time, there will be confusion, because this A and the clock changing, maybe the previous value will be taken. So, A must be applied a little before the clock is coming, stabilized, and then you apply the clock, then only the correct value of A will be shifted into the register, right. This is what I mean to say. So, now let us see this. So, what I have done here, I have initialized clock to 0, because I have not given a delay, it is at time t equal to 0. At time 2, I have set clear to 0. At time 5, I again had set clear to 1. So, I have cleared the register at time 5, because you see clear was a negate clear. So, here it was negate at time 0. So, at time t equal to 0 the counter would be cleared. So, at 5 again I am releasing the clear, making it 1. Well, and then I am saying at 5 clock equal to not clock. So, let us try to see what is happening here. So, I am generating a clock signal like this. This is clock. So, at time 0 I am making it at 0, this is time 0, and at 5 always at after delay 5 clock equal to not clock. So, after delay of 5 I am making it 1, after another delay of 5 10 I am making it 0 again, at 15 I am making it again 1, 20 again, 25 and so on, like this the clock is changing, right. Now, here in between what I have done, I have set clear to 0 at time 2. So, at time 2, let us say somewhere here, this is time 2, I have made clear equal to 0, and again at time 5 I have made clear equal to 1. At time 5 I have again made clear equal to 1 and I leave it at 1. So, what it means is that during this period the counter will be cleared, because it has got a 0 edge here, it has become 0 out here. Okay? Fine. Now, what I am doing here, let us see. These 4 bits 0 0 1 1 I am shifting. In this initial block I am initially giving a delay of 2, right. Then after delays of 10 10 10 10 I am shifting the 4 bits 0 0 1 1. What does this mean? Let us see now. So, we are giving an initial delay of 2. So, initial delay of 2 means we are here 2, this is 10, this is 20, then you are giving a delay of 10 after that, that means it will be here at time 12, then again we are giving a delay of 10. So, it will be here 22. So, you see after the falling edge comes I am applying the next input here. So, this in, the first in equal to 0 I am applying here, at 12 I am applying 0, then at 22 I will be applying again a 0, then at 32 later on I will be applying a 1, then again at 42 later I will again apply a 1, 0 0 1 1. You see the points I am applying, I am ensuring that when the next clock edge comes the input is absolutely stable. When the next clock edge comes it is stable. You see, just look at the next one also, 20. So, when the next clock edge comes this input is stable. So, there is no confusion of this edge with the input varying, right. So, we have written our test bench in such a way that these delays are automatically adjusted. The inputs are stable just well before the clock edge comes. Clock edge is coming at 15, but at time 12 my input is stable. Clock edge is coming at 25, at time 22 my input is stable. It is coming at 35, at 32 it is stable. Okay? And in the here in the last initial block of my code, we have just specified the dump file and said that at 200 we will finish. So, you just see the waveform, this is what I wanted you to see. You see clock, this is the clock signal which I am showing. Clear, you see clear, there is a small gap here. So, at time 2 it has become 0. So, when it has become 0 all A, B, C, D has become 0, it has cleared. A is 0, not A, B 0, C, D, E, this 4 shift register outputs have been cleared. Now, the thing will start from time 12. So, this is 10, next clock when it comes, you see here it will start counting. This A is 0, 0 will be shifted. So, you apply 0 here, 0 will be shifted, apply 0 again, it will be shifted, then you apply A1, 1 will be shifted, and then apply A1. You see these are getting shifted 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1, they are getting shifted. A is getting B, B to C, C to D, D to E. Okay. So, this will go on. So, you see it, this 0 0 1 1 I am repeating 2 times, repeat 2. So, 0 0 1 1 0 0 1 1, that is why you see 0 0 1 1 0 0 1 1, then it remains 1 and it nicely gets shifted, right, fine. So, now let us take another example. So, it is a 7-bit binary counter. So, clear clock and count. So, at neg-h clock, whenever clock is going from 1 to 0, if synchronous clear, clear is 1, I am clearing, otherwise incrementing. So, the test bench we are writing like this. So, for counter it is very simple. So, initially we are saying clock equal to 1 in one initial block. So, in another always block, after a delay of 5, clock equal to not clock. So, in the last initial block we are specifying the dump files and we are saying the monitor, we want to see time and count value, and here we are specifying that initially we are clearing the counter and at time 15 we are making it 0 again. So, the counting should start from time 15, till then clear was 1 and it will continue till 200. So, at 200 again I am setting clear to 1, it will be again cleared, then after time 10 I will finish. So, if we again simulate this code, similarly you will see that the output generated will be like this. You see you are monitoring time and count. So, there is the time and there is the count. The time will go from 0 and count will start. You see here before 15 count will not start because it is cleared. So, only after 15 next clock comes it will start counting. So, you see, so from 20 the count starts increasing, then clock period is 10, 30, 40, 50, 1, 1, 1 it is incrementing. So, again, so it will continue till 200, 200 you are again clearing it. So, after 200 after time 10 it becomes 0. So, the timing diagram if you view it will look like this. You see clock is coming, this is clear, the clear will be cleared at time 15, till then the count value was 0, you see 0 0 written here. Then with every clock falling edge it becomes 0 1, next falling edge 0 2, 0 3, these are the count values. This is shown in hexadecimal 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F and so on, it will continue. Okay. So, the counter is counting correctly, you can see, verify. Okay. Now, we are taking an example where we want to verify the output automatically. So, we take the example of the simple full adder again, full adder, sum and carry. Let us say we write the test bench like this. We write the test bench as follows. We instantiate the full adder, we declare a variable called correct of type integer, initialize it to 1 in the initial block, correct equal to 1. Then at time 5, let us say after delay 5, we apply A1, B1, C0, right. Well, we give a delay, then we check for AB, say 1 1 0, this sum is supposed to be 0 and carry is supposed to be 1, right. So, we are checking if sum is not equal to 0 or carry is not equal to 1, then you set the variable correct to 0. Then apply the next vector 1 1 1, again give a delay, then if sum is not equal to 1 which is supposed to be, carry is not equal to 1, then again you set carry to correct to 0, and then the last vector 0 1 0. 0 1 0 is supposed to be give sum 1 and carry 0. So, if sum is not equal to 1, carry not equal to 0, correct equal to 0. At the end you just display correct. So, it will be displaying either 0 or 1. So, if everything is correct, the full adder design is correct, then you should get a 1 in the output. but if any of the outputs are not matching, then you should get a 0 as the output, right. So, this is a self checking test bench. You can verify the output and compare and print the summary result directly. Okay. Now, the last example I take is one of generating random test vectors. Now, here let us say we take an adder example. There are two 8-bit numbers A and B, the output is an 8-bit sum and C out is the carry. So, this is a behavioral description, carry out and out, the 9-bit sum with the carry is equal to A plus B. Now, we want to test it with some random input patterns A B. There is a function called $random or task, sometimes called also, which can be used to generate a random number. This function can be called with a parameter seed also. This is optional, you may or may not give this seed. So, if you give a particular seed, it means that the same sequence of random number will be generated every time, so that you can rerun and reproduce the test. You can verify whether it is working in the same way. But if you do not give a seed, then it will be really a random thing. If you run it again, some other input will come. So, let us see the example. Here, see here we have instantiated the adder add A B, these are reg, these will be the inputs to the adder, and sum I have declaring as var, this C out is also a var, and I declare an integer called my seed. So, which I initialize to 15, initial my seed 15. So, in this initial block I repeat 5 times, I apply 5 random patterns, repeat 5. This is what I do. A equal to $random my seed, I generate a random number, put it to A. So, I put another random number, put it to B, give a delay of 10, then display. What I display? Time t, A, B in hexadecimal and sum also in hexadecimal. So, you see at time 10, the first random number that was generated was 0 0 and 5 2. So, if you add them, sum is 5 2. Second time it was C A and 0 8, say A and 8 is B C D E F 0 1 2, it will 2 and carry it will make D. Similarly, 0 C and 6 A is 7 6, B 1 and 7 if you add, sum will be 2 2, there will be a carry out, 2 3 and D F if you add, sum will be 0 2. So, in this way you can generate random numbers and you can just apply it to your design under test. So, with this we come to the end of this lecture. Well, we have seen a number of examples of writing test benches. Of course, this is not the end of thing, we will be taking more examples later, and whenever we talk about a design, we shall also be showing the test bench side by side. So, you will always be getting a flavor of something new on the test benches that we will be discussing in the future also, but till then we stop for now. Thank you.